Hello, welcome to my channel. In this video, we are going to be looking at rotating mass on a table or a flat horizontal plane. So, the problem that we are going to be looking at um, is depicted in this figure below. So, from this diagram, we can see that we have M1 rotating on the table. Then this mass M1 is attached to mass M2 by a string. So the radius of this particular circle is R. So the question that can come out from this kind of problem is, what speed must M1 have for the system to remain in equilibrium? So if this mass is not rotating and M2 is greater than M1, one would expect that the system will slide downward. So, but once this particular mass undergoes rotation, right? There is a particular speed that this M1 must have for this system not to move. That means for this system to remain stationary, or for this system to remain at equilibrium. So for us to calculate the speed, we must consider the equations for these two systems. So let's consider the first system, M2. For M2, we realize that there is a tension in this string and acting against the weight of this mass, M2. So for that kind of case, we say that the sum of all the forces upward must be equal to the sum of all the forces downward. And all the forces acting downward is just the M2 times the weight. And the forces acting upward is just the tension. So we have sum of forces along the y-axis is m2g minus t equal to 0. That is, m2g acting downward minus t acting upward must be equal to 0. And from this point, we can make t the survey formula, and we have t equal to m2g. So this is the equation for this system. Let's consider this other system undergoing rotational motion, right? And it is believed that any particle undergoing rotational motion, the sum of all the forces acting towards the center of that particular circle must be equal to a particular formula, which is given as sum of all the forces acting towards the center of that circle must be equal to this formula, mv squared all over r. Our m here is the m1, and all the forces acting towards this is equal to the tension, because the tension in this string also corresponds to the tension in this one. So for that case, we have this expression. But we have established that T equal to m2g. Then we can replace our T here with m2g, and we get mv1 squared all over r equal to T equal to m2g. So we are no longer interested in this. We'll just equate this and this. So now we have m2g equal to m1v squared all over r. So at this point, we can make v squared the survey formula by taking r to this side, and we have this. So if we now make our v the survey formula, we have this. So this must be the velocity of m1 for the system to remain in equilibrium. So if you analyze this particular one properly, you discover that once m2, the mass of this and the mass of this are equal, the velocity will just be square root of g of r times r. So what we'll notice is that the greater the mass of m2, then the higher or the greater the speed that must be, that m1 must have for it to remain at equilibrium. But the greater the value of m1, that's if this one is higher, the mass of this is higher, then the velocity will be smaller. So vice versa, whichever case you consider can always determine the velocity of this particular object for it to remain in equilibrium. I hope this helps. Please like, share, and subscribe to this channel. Thank you.